Hi, let's continue with canonical transformations. So we'll first see how we can find the transformed Hamiltonian. We'll do an example problem here. Right? So the transformed Hamiltonian is found by this relation k is equal to h plus dou f by dou t, where f is the generating function. Now if f does not depend on time explicitly, then we simply have k is equal to h. Okay, but you should remember, after finding k equal to h, you should remember to put it in terms of capital Q and capital P. Right, you have to write it entirely in terms of capital Q and capital P. Right, that's the only thing you have to be careful about. Let's look into the first problem. A particle of mass m moves in a one-dimensional potential V of q and is retarded by a damping force minus 2m gamma q. The Lagrangian is given by L is equal to e raised to 2 gamma t half mq dot square minus v of q. So the Lagrangian is given and we need to find the corresponding Hamiltonian first. So the first part of the problem is to find the corresponding Hamiltonian. Now in the second part of the problem, we are given a generating function. We need to find the transformed Hamiltonian here. V of q, if you substitute V of q equal to half m omega square q square. Alright. So in the first part of the problem, we need to find the Hamiltonian corresponding to the Lagrangian. Right. In the second part of the problem, a generating function is given. We see that it explicitly depends on time. Right. So we have to find the transformed Hamiltonian corresponding to this transformation. Also, if the potential energy is half m omega square q square. Okay. Alright, so the first part of the solution, we have done these kinds of problems to find the Hamiltonian. In the first part of the problem, the Lagrangian is given like this. We need to find the Hamiltonian. We know how to find the Hamiltonian. First, you write down the expression for P, that's dou L by dou Q dot, and the Q dot appears only here, and there's an e raised to 2 gamma t here. So P is equal to dou L by dou Q dot, that's equal to 2 e raised to 2 gamma t mq dot. Okay, and from here you find q dot in terms of p. Yeah, that's the usual procedure, and q dot is p by m e raised to minus 2 gamma t. Now to find the Hamiltonian, we can find the Hamiltonian by the relation h is equal to p q dot minus l. Right, we are talking about one dimension, so it's just p q dot minus l. Right. Alright, so we find p q dot minus l here, and then you should be careful that in the final answer, there shouldn't be any terms involving q dot. We should write it entirely, or we should get rid of all q dot in favor of p. Okay, so that's the steps we do. We do this thing. It's p q dot minus l. You substitute for q dot from there, and then you get this answer: h equal to p square by 2m e raised to minus 2 gamma t plus e raised to 2 gamma t v of q. Right. So we combine these terms. All right. Okay. All right. So we have got the Hamiltonian. You can check this. You can check the steps. We don't want to go in detail with these steps, but because I think we have done these kinds of problems in some detail earlier. Right. So we have found the Hamiltonian. Okay. We see that Hamiltonian is a function of p and q, as it has to be. Right. In the second part of the problem, we put v of q is equal to half m omega square q square. Okay, that's our v of q, and now we have to find the transformed Hamiltonian for a given generating function. Right. So what's our f here? Let's just check for f. F is e raised to gamma t q p. All right. So f is equal to e raised to gamma t and small q capital P. All right. Small q capital P. Alright, now we know that k is equal to h plus dou f by dou t. So what's dou f by dou t here? H we already write down, p square by 2m e raised to minus 2 gamma t plus e raised to 2 gamma t v of q. And what's dou f by dou t here? It's simply gamma. It's a gamma here. Gamma e raised to gamma t multiplied by q p. Right, dou f by dou t. Right, but now we see that this is all in terms of small p and small q. Now the final step is to write k as a function of capital Q and capital P. Okay. For that we need the transformation equations, and given the generating function, how do we find the transformation equations? Right. So here we see that our transformation function has this form. It's in the form small q, capital P and t. Right? What are the transformation equations? We know the transformation equations can be found like this. P is equal to dou F by dou Q, and here we already have a P, so the corresponding capital Q is equal to dou F by dou P. Right? So here it's a coordinate in the first position as it has to be, so there is no minus sign. Also here it's a momentum in the second position, so no minus sign here either. So these are the transformation equations. Okay, you may have to invert it, you may have to shift around a little bit, but from these equations you can obtain the transformation equations. Okay, what we need actually is P as a function of Q and P, also Q as a function of Q and P. Now then we'll substitute it all in here. That's what we'll do. Alright, so here is F, and what small p is dou F by dou Q, it's e raised to gamma Tp, and capital Q is dou F by dou P, right? That's e raised to gamma T multiplied by Q. Okay, so from here we see that small q is equal to e raised to minus gamma T multiplied by capital Q. So we have got small q in terms of capital Q. Okay, alright, what about capital P in terms of small p? So from here we can get it's already given. All right, small p is written in terms of capital P, so this is already there, we can directly use it. Now what we do is that we use this, okay, small p as a function of capital P and small q as a function of capital Q, and then we'll substitute it in the k that we found here. All right, also we need to substitute what do you say, v of q is equal to half m omega square q square. Okay, that's exactly that we do what we do here. So instead of small p here, instead of small p, you can write it as small p square. We can write it as e raised to 2 gamma t capital P square. Okay, and there is already an e raised to minus 2 gamma t here, and this is actually capital P. All right, this is capital P. So it's capital P square by 2m plus what about it's e raised to 2 gamma t multiplied by v of q. Okay, and what was v of q? V of q is half m omega square q square, and that in terms of capital Q, that's simply half m omega square e raised to 2 gamma t capital minus 2 gamma t capital Q square. Okay, so that's v of q for us, and then you have got e raised to 2 gamma t here, that will cancel with this e raised to minus 2 gamma t. All right, and you will simply get m omega q square divided by 2. Okay, that's not all. We have got this extra term here. It's gamma e raised to gamma t multiplied by small q small p. So what's small q small p for you? It's e raised to minus gamma t capital Q multiplied by e raised to gamma t capital P. Okay, so that will just cancel off and you get p square by 2m plus half m omega square q square plus gamma q p, all in terms of capital Q and capital P. So this is the transformed Hamiltonian for you. Okay, this is the final answer. All right, so a common mistake that people may make is to stop at this point. All right, don't stop at this point. Always write the new Hamiltonian in terms of capital Q and capital P, the transformed coordinates and momenta. Okay, that's it. It's not a very difficult kind of problem. It's easy. Right? So if such problems are asked, you know what to do. Alright, the next kind of problem is to find the generating function given the transformation. Right? How do we do this? So one way to find it, we already did this in a problem. We can write df as pi dqi minus pi dqi, alright, and then you will get something. Alright, df is equal to d of something. Right? So the generating function will be whatever is in here. We have already seen this, right? But this doesn't give always the kind of generating function that we need. All right, sometimes you need a generating function of type 1, and other times you may need a generating function of type 2, etc. So I'll just enumerate the steps that we need to follow to find the generating function. Okay, and then we'll go on to problems, and you'll understand these steps a little bit better when we do the problem. But let's first go through the steps. Okay. So first thing is to write down the transformation equation for the type of generating function that we need. Okay. So they may ask you to find the generating function f of small q comma capital Q. All right, or they may ask you to find f2. All right, f2, or simply f of small p comma capital P. Yeah, they may ask you like this. Right. So the first step is to write down the generating function corresponding to this given function, generating function. Okay, not given generating function, the kind of generating function that you need to find. For example, imagine they give you a transformation and they ask you to find f1 of small q comma capital Q. Okay, so the first step is to write down the transformation equations. So we write, in this case we know that the transformation equations are small p is equal to dou f by dou q and capital P is equal to minus dou f by capital Q. Okay, dou capital Q. Right, we know this. Right, there's a minus sign here because the position, a coordinate appears in the second place here. That's it. Okay, so we have got the transformation equations. What do we do next? Right, the next step is to use the given transformation to write small p and capital P as functions of small q and capital Q. Okay, all right. So we assume that in the question a transformation will be given, a particular transformation will be given. Okay, so we can play around with that, we can transform them. Okay, and what we do is that suppose you need to find small q f1 as a function of small q comma capital Q. If this is what you want to find, you will use the transformation given in the question and write this small p as a function of small q and capital Q. Okay, I hope this is clear. And then you will write this capital P as a function of small q and capital Q again. Alright, I'll repeat these steps. The first step is to write the corresponding transformation equations. The transformation equations corresponding to the given type of transformation that you need to find. Okay, that's the first step. Suppose they ask you to find f1 of small q comma capital Q. Immediately you write down the transformation equations. Alright, that's not all. The next step is to write this small p. Now you will have to use the transformation equation given in the problem, and then you will write this small p as a function of small q and capital Q, or whatever functional dependence that you need. Alright, whatever functional dependence that you are asked to find. Right, so you'll use the transformation equation to write small p as a function of whatever appears here. Alright. Okay, the next step is to integrate. So we have got these equations now. These are the differential equations obeyed by our generating function. These are the differential equations obeyed by our generating function. Now it's only a matter of solving these differential equations to find the generating function. These are partial differential equations, so we have to be careful. It's a matter of integrating. Alright, so we take the first equation. First we take the first equation. Alright, this is a differential equation. This is a partial differential equation obeyed by this capital F. Alright, this generating function. Alright, so from here we see that we can write f of q comma capital Q. This is equal to integral p of q comma capital Q multiplied by dq. Is that all? No. This gives you only one part of the dependence. Alright, it might give you this q dependence, small q dependence. Alright, so since this is only what is a partial derivative with respect to small q, when you integrate, you could always have some function of capital Q here. When you integrate, you could have a function of capital Q here, right? Because when you take the partial derivative, this integral will disappear and it won't affect this term. Alright, so in principle there should be an extra term here. It's just like adding a constant. Alright, when you make an integration, you can always add a constant. In this case, since it's a partial derivative, alright, we can have, instead of a constant, we could have any function of capital Q here. Alright, so you have to be careful to add this term. In most cases, this term can be set to be 0. It will be a constant and it can be put equal to 0. But in some cases, you will have some function of capital Q here. You can have some function of capital Q over here. Right? So in order to fix this thing, in order to fix this f of capital Q, we'll use the second equation, the second transformation equation. Alright? So basically, we'll integrate this, and whatever result that we will get, we'll substitute it in this equation, and then that will allow us to fix this small f of capital Q. Alright, I hope this is clear. So this is a partial derivative with respect to small q only. Alright, so when you integrate this, you could be missing out some function of capital Q. That's why we write this plus f of capital Q over here. Right, I hope this is clear. So I think you will understand it better when we do a problem. So let's go into a problem. All right. And you have to find small f of capital Q by using this equation. All right, we'll integrate the first one, or you could integrate the second one and then use the first one, or whichever way you like it. All right, maybe some integrations might be easier, so you can choose the easier integration. All right, so the steps are exactly the same. All right. All right, now let's do a problem, okay, to demonstrate this procedure. Find the generating function f of small q comma capital Q. So this is of the first type, this is of the first type. For the canonical transformation given by, so the transformation is given Q, capital Q is equal to P inverse, capital P is equal to Q P square. All right. So what was the first step? The first step was to write the transformation equations. Okay. So the transformation equations in this case, this of type 1, so it's exactly the same. Small p is equal to dou f by dou q. Yes. Capital P is equal to minus dou f by dou q. Right. That's the first step. The first step is done. You just write down these equations, all right, for the given type of generating function. We know how to write this equation. We know how to fix this sign. All right. Okay. Now, what's the second step? The second step is to write the small p as a function of, what's the generating function you need to find? You need to find the generating function as a function of small q and capital Q. Right. So next step is to find this small p as a function of small q and capital Q. Similarly, this capital P as a function of small q and capital Q. Okay. So that's what we need. So you look at the transformation equations. From here you see that P is equal to Q inverse. All right. And then you will put this here. Capital P is equal to Q multiplied by, Q is already P, small q. Okay. Small q multiplied by P square. P is Q inverse, so it's Q raised to minus 2. Okay. So again we have got capital P as a function of small q and capital Q as we need. Okay, that's the next step we do. All right. We have got dou f by dou q is equal to Q inverse, and dou f by dou q is equal to minus Q, capital Q raised to minus 2. Okay, that's what I said, I think. Yes. All right. Okay. Yes. Is there a minus sign that I missed somewhere? No, that's correct. Right. So you remember that there's a minus sign here, and you have to be careful to keep that minus sign. All right. Now we have got the partial differential equations obeyed by the generating function. Now it's just a matter of solving these equations. All right. Okay. All right. So in this case, what you need to do is, here you can say that from this you can say that f is equal to integral p dq, because it's a derivative with respect to small q, and then you could have some function of capital Q here. Right, that's what we do here. F of small q comma capital Q is integral p dq plus f of q. Now we substitute for the small p that we already found in terms of capital Q and small q, whatever. Right. And you have got this P is equal to Q inverse. You substitute that here. It's Q inverse dq plus f of q. You still could have some function of capital Q here. All right. So this is, if you integrate q raised to minus 1. Okay. What do you get if you integrate q raised to minus 1? Okay. So this q raised to minus 1 will remain exactly the same, and you have got this dq. Right. So when you integrate with respect to small q, capital Q looks like a constant. Right. You don't have to worry about it. Right, because we are talking about partial differential equation. So this is simply Q inverse multiplied by small q and then some function f of q. Now the next step is to fix this f of capital Q. The next step is to fix this f of capital Q. For that we use this equation. Right, we demand that dou f by dou capital Q is equal to minus q raised to minus 2. Alright, so you plug this in here and you see that dou f by dou q. What's dou f by dou q? If we use this, it is q raised to, this minus q raised to minus 2. Okay, minus q raised to minus 2, and this small q will remain there. Okay, plus dou small f by dou q, taking the derivative of this whole thing. Right, this is equal to minus q raised to minus 2. Right. So when you compare this, you see that it's exactly the same thing. q raised to minus 2 q, q raised to minus 2 q. Okay, there is also the minus sign. So this means that dou f by dou q is equal to 0, or f does not, this means that f does not depend on capital Q, right? So you could fix this, you could put any constant there, it doesn't matter. So you can as well put it equal to 0. It means that if it does not depend on capital Q, it means that it's not going to change your transformation equations. Okay, so you can just put it equal to 0 over there. Okay. The next problem again is to find a generating function of type 1, all right, which means that you need a function that depends on small q and capital Q only, right, for the following canonical transformation. Right? So the canonical transformation is given. Now for the first step, as we said, is to write down the transformation equations, all right, generated by this particular function or the relations. So we know that we know how to write this relation. Small p is equal to dou f1 by dou small q, and capital P is equal to minus dou f1 by dou q. Fine. What's the next step? The step 2 is to find small p, write small p in terms of small q and capital Q, because that's the functional dependence that we need here. So for this you will have to make use of the transformation equations given here. So from here you see that it's easy to solve for small p, because p sine alpha from here, this is equal to, p sine alpha is equal to q cos alpha minus capital Q, right? So from here you see that small p, we got the first equation immediately because this is already a function of small q and capital Q. Okay, so small p is equal to q cot alpha minus capital Q cosecant alpha. Okay, divide throughout by sine alpha. Okay. Now we need capital P as a function of small q and small p. Small q is here, sorry, small q and capital Q. We have got small q here, we don't have to do anything to this term, but this we have to write in terms of small q and capital Q again. Right? We don't need any small p in here. Okay. So for this capital P, this can be easily done because already we found the small p here. You substitute small p in terms of small q and capital Q in here. Okay, and then this is easily done. You just have to solve it, just have to simplify it. That's exactly what we do here. You get p, small p is equal to q cot alpha minus capital Q cosecant alpha. Fine. Okay, and capital P is equal to q sine alpha plus p cos alpha. That's the given thing. We don't need this small p here. The small q is fine, so let's keep it there. So q sine alpha plus, what's the small p? It's q cot alpha minus capital Q cosecant alpha. All right, this is the small p, and then we have got a cos alpha here. That is just this cos alpha. Okay, now we can just simplify this. You can multiply this cos alpha inside, then this becomes cos square alpha by sine alpha. Okay, so you can pull this q outside, and then it's cos square alpha plus by sine alpha plus a sine alpha from here, and then minus q cot alpha, because this cosecant alpha is 1 by sine alpha, so that is cos alpha by sine alpha again becomes a cot alpha. Okay. Now if you do this, you see that you can take the LCM and add these things. So it cos square alpha plus sine square alpha becomes 1 by sine alpha becomes cosecant alpha. So our final answer is capital P is equal to q cosecant alpha minus capital Q cot alpha. We have got our capital P as a function of small q and capital Q. That's what we needed, right? So, and from here we have got our small p as a function of small q and capital Q, right? Now we go to the third step, right? We use the small p and capital P that we found here in this equation, right? Now we write this p as a function of small q and capital Q. Similarly, we write this p as a function of small q and capital Q, and then integrate. Well, that's the next step. Okay. So we'll take the first equation. Small p is equal to dou f1 by dou q, and that's equal to q cot alpha minus q cosecant alpha from here. Okay, from here q cot alpha minus capital Q cosecant alpha. Now we integrate this. F1 is equal to, this is just a constant, so we don't have to worry about that. When you integrate with respect to small q, Okay, this becomes q square by 2. So it's q square by 2 cot alpha minus here it's dq, integral dq, all right? Just integrate by dq. And then this capital Q remains the same. We are talking about partial derivatives. So it's capital Q multiplied by q and then a cosecant alpha, right? And remember, we have got two equations. We are only integrating with respect to small q. So there could be some function of capital Q in here. How do we find this function of capital Q? Right? We take this as f1 and then check whether we'll get this particular equation for capital P. Right? So you substitute in here, right? So we have got dou f1 by dou q has to be minus P. Okay, so you find dou f1 by dou capital Q from here, right? This term doesn't appear here. It comes minus q cosecant alpha. You're just finding dou f by dou capital Q. So it's minus q cosecant alpha plus there's a dou f by dou q. Okay, it's actually dou f by dou q. All right, it's actually dou f by dou q, and this is equal to minus q cosecant alpha. Okay, why? Because this is our capital P minus capital P. So this is all right because we need minus P, right? We have put this minus to this side. So you just substitute for P here with a minus sign. So it's minus q cosecant alpha plus capital Q cot alpha. Okay, is this true? So from here you see that these terms are the same. From here you see that dou f by dou q, right? You could also write partial derivative here just to be consistent throughout, right? It doesn't really matter because you'll see that this function depends only on capital Q. So whether you take the partial derivative or the total derivative, it's the same thing. But let's not worry about those things here. So df by dq is actually q cot alpha here. It's capital Q cot alpha. Now you can integrate this f of capital Q. You integrate this and you get q square by 2 cot alpha. Okay, this is clear, I hope. Now this is the way we found. So here in the previous problem, we could just get rid of this thing and put it equal to 0. In this case, we cannot. Right? So if you do just one integration, you are in the danger of missing out this particular term. All right. So f of capital Q here is q square by 2 cot alpha. Right. You just put it back in here. Okay. Sorry, just put that back in here, and you have got the generating function. All right. So you just add this q square by 2 cot alpha here, then we are done, right? You can maybe simplify a little bit, make it look a little bit simpler. I can pull this half outside and cot alpha outside and write as q square plus capital Q square, and then there is a minus q cosecant alpha. Okay, that's exactly what we have here. We have done this. Right? So we have done two types of problems. In one type of problem, the extra function could be set equal to 0. In most problems, we can do that. Okay, but in some problems this extra term is non-zero. You cannot set it equal to 0 and you have to be careful about it. Okay, the rest of the problems I think I leave as exercises to you. The solutions are given here. The steps are exactly the same. I'll just go through them quickly and then leave the rest of it as exercise for you. Now for the examination, if the options are given, right, if the options are given and the transformation are given, the first thing you could try is to always find this dou f by, use the transformation equations. You know the transformation equations, okay, like you know how to write. In this case, for example, small p is equal to dou f1 by dou q and capital P is equal to minus dou f1 by dou q, right? So you can do this thing. Okay? You can actually check all the options. Okay, in your examination, what you need to do is check all the options with the transformation equations of the corresponding type, with the correct transformation equations, and if you get the answer, if you can get back to the question, then that's an easier way to do it. All right. So for your examination, maybe you don't have to go through all these steps. You just check. You know how to write down the transformation equations corresponding to a given type of generating function. You can just check. All right. So maybe that will help you get along a little bit. All right. Okay, now that's how we do these things. In the next problem, a canonical transformation is given, capital Q is given, capital P is given. In this case, we need to find the generating function, which is a function of small p and capital Q. Okay, again, the first step is to write down the transformation equations, small q and capital P. Now, we need a function which is, we need a function which is function of small p and capital Q. So next step is to use the transformation equations and write down this small q as a function of small p and capital Q, this capital P as a function of small p and capital Q. Okay. So from the canonical transformation, you can easily get that. The next step is to integrate. Of course, there will be an extra term here. Now you have to fix this extra term that you can use. You can do it using the second part of the equation, right, or the second partial differential equation, and you will get this answer. So this is left as an exercise. Okay. The next one is also left as an exercise. Right. Here you are again asked to find the first type of generating function. We have already done such problems, so you can go through it. If you have any doubt, you can please contact me. Okay. Now, just to conclude, I'll give you the types of generating functions. All right. You have to remember this. You see that we can actually relate these by Legendre transformations. Okay. So sometimes they may ask you to find simply f1 or f2 or f3. Then you need to know what's the functional dependence of f1, f2 and f3. Okay. So f1 is a function of small q, capital Q and t. All right. For f2, you just change this capital Q to capital P. That's all. You change one thing at a time. Right. So you can actually go from f1 to f2 by Legendre transformation. All right. We have done this Legendre transformation. So second one is a function of q, capital P and t. Right. That's done. Now again we start from here and then change small q to small q to small p. That's all. Okay. All right. Now the only thing left for us to do is change both small q and capital Q to the corresponding small p and capital P. That would be f4. All right. So f1 is a function only of the old coordinates and the new coordinates, and f4 is a function of old momenta and new momenta only. Okay. In between are f2 and f3. So it's a good thing if you can keep this in mind. Remember this, because in case they ask you to find, they may ask to find f of q comma capital P. Fine. If they ask that, we know how to do that. Right? But they may also ask find f2. Right? Find the generating function of type 2. They may ask, and then you will need to know what kind of generating function it is. Right? So with that, we'll wind up this session. I hope you can solve the problem. I have just given one more exercise to find the transformed Hamiltonian. Generating function is given, you need to find the transformed Hamiltonian. That's an easy exercise, so you can try it. Okay. All right, with that we'll wind up this session. Thank you.